Okay, welcome to lecture here. We're continuing on chapter 14. I think it's about where we left off. Get started here in just a second. Okay, so we've been talking about chapter 14. A reminder that this is not going to be on the exam next week. This starts sort of, I guess, exam 2 material, if you will. So in chapter 14 here, we started talking about acids and bases. We talked about sort of a couple of definitions, sort of a um, early definition was one where we still sort of think about it that way, is that an acid is something that's able to produce H plus or H3O plus. So remember sort of an acid base chemistry, H plus, which is the hydrogen ion, and H3O plus, which is the hydronium ion, pretty much the same deal. So they're used interchangeably, both in formulas, also both in sort of equations, if you will. They're sort of used interchangeable. So something that's really able to produce H plus, H3O plus, and you see that usually in the equation, obviously on the product side, means that it's usually some type of acidic type solution. While something that has the ability to produce hydroxide OH minus is considered a base, and same idea. So uh, something really important to keep in mind as we go through these next several chapters that sort of involve acids and bases and stuff like that is really that aspect of it. Very often people have trouble figuring out, is it sort of acidic? Is it basic? Should I be doing sort of the calculation, acidic or basic? And again, as we talked about last time, writing the equations properly and seeing what you have on the product side can be super helpful in the calculation part. So, although it may seem like maybe those two aren't necessarily connected a lot, it's really important to get those equations down correctly, because when you look at the equation, it does tell you a lot of information. And that's a big sort of key information that you could get from an equation, is just that. If you again look on the product side, you see H plus sitting there or H3O plus sitting there. It's like acidic, and you should be doing sort of, I want to say acidic calculations, but calculations that involve acids and stuff like that. And same idea there on the product side. If you see hydroxide sitting there, it's probably basic. So you should be doing some sort of basic sort of calculations, or calculations that, involve sort of bases. So really important, to keep that in mind as we go through this chapter and maybe the next chapter and so forth. Um, that's something that gives people a difficult time, is that aspect of it. So those were pretty good sort of early definitions by Arrhenius. They were kind of limited because he really did focus in on bases that only really contain hydroxide. So along came Bronstead and Lowry with a more sort of general definition of a acid or base, and they looked at acid or base really as sort of this guy here, our proton. And again, H plus is also considered a proton in acid base chemistry, again, because hydrogen has one proton, one electron, and no neutrons. So in order for it to become positively charged, it has to lose the electron, and thus is left just a proton. So a proton is pretty much an H plus. H plus is pretty much, H3O plus. So again, those three sort of words used a lot of times interchangeable in acid base chemistry. They all basically are representing, I guess I said basically there, but basically representing an acid, really, is what it's representing. And when we talk about Bronsted-Lowry definition of acid and base, a Bronsted-Lowry acid is a proton donor, so it's something that will give away an H plus, while a Bronsted-Lowry base is a proton acceptor, which will accept an H plus. And that also is something that people mess up on. Again, it's not just the H that is sort of being transferred there. It is the H plus. So that plus charge has an effect on the overall charge of what you get. And sort of a consequence of sort of the Bronsted-Lowry definition of acids and bases is that you do create what are sometimes referred to as acid-base conjugate pairs. And you basically get partners, and you get partners from the reactive side to the product side, where the only difference, as we talked about last time, that there can be is 1H plus. So you get two things that are basically related to each other on opposite sides of the arrow, and they are related to each other by a 1H plus difference. And in certain cases, there'll be one more H plus or one less H plus. And they're sort of opposites in terms of their relationship. So if you have the acid on the reactant side, its partner on the product side is the conjugate base. And again, the difference between those two would be if you have the acid, it would donate its H plus, so it would have one less H plus on the product side. While if you have a base on the reactant side and its partner on the product side will be the conjugate acid, and again, the difference there is the base is going to accept the H plus, which means the conjugate acid will have one more H plus. And as we talked about last time, just your run of the mill, I guess the way to put it in, acids and bases are always found on the reactant side, and your conjugate acids and conjugate bases are found usually on the product side of the arrow, and those two relationships. Now, as we sort of alluded to at the very end here, I think last time when we were kind of looking at the H2SO4 sort of example, H pluses or protons, they really do come off in a stepwise fashion, and we'll talk more about that later in this chapter when we talk about diprotic and polyprotic acids. But they do come off basically one H plus at a time. And for example, like the H2SO4 that I did here at the very end last time, the first thing that will happen is this guy will lose the H plus, and then that one with the HSO4 minus will lose the second H plus. And that is why, as we mentioned at the very end, these two guys, again, are related to each other. They're partners. Our original guy and that first guy are also partners. But if we go from the H2SO4, like it was in this question, to the SO4 2 minus, that is two H pluses, and that is too much for them to be partners. Any questions on what we talked about there last time? Okay, so I think we did this example. So I think you have this one here. So aniline is isolated. What is the formula of the conjugate acid? So take a second there and figure out what the formula of that conjugate acid would be. That is correct. The test is on Thursday of next week. Okay, so if we want to write the conjugate acid, a good way to do this, if they weren't nice enough to tell you what things are, is just think about the relationship we talked about. We have an acid, we have a base, and we have a conjugate acid and a conjugate base. And the relationship is the acid on this side, its partner on this side is the conjugate base, the base and its partner on the other side is the conjugate acid. So in this particular case, they asked us to write the formula for the conjugate acid. And if they weren't nice enough to tell us that this is a base, we can work our way backwards and go, what we are looking at is a base. And what that means is a base should accept an H plus. So we essentially should take this guy and put an H plus on. And you'll end up with something like that, which I think is number 2. Looks like a winner on that one. Question on that there. So sometimes it's really helpful to sort of think about things in the backward sort of sense of where it came from, and then just use the generic sort of definition of that. So for example, if you had HCO3 minus, write the conjugate acid for it, and why don't you write the conjugate base for it? Okay, so same idea. So we can kind of work our way backwards. So let's start here with our conjugate base. So if I'm looking for a conjugate base, that means in this particular case, what I am starting with is an acid, which means that this guy should give away the H plus, and we should end up with CO3 2 minus. Now, if I'm doing the other, which is the conjugate acid, like we had in the previous problem, that means, as we saw in that previous problem, what I am dealing with in that case is a base, and its conjugate acid should be H2CO3 by putting on the H plus and subtracting the H plus on this side. Question on those two examples. Now, we do see something here that can act as both an acid or a base, and that oftentimes happens when you got something with a hydrogen and like a charge. And that is something that is known as an amphoteric substance. So an amphoteric substance is basically something that could act as an acid or a base. So there are certain things that you'll come across that has the ability really to kind of go both ways, either in certain cases be an acid, in other cases be a base. And we'll talk about ways you could sort of identify what's going to happen or sort of choose which way it's going to go. But there are definitely things that could kind of go both ways. Question on acid conjugate base pairs, how to write them, how to figure them out.
I'm sorry. So, what is the relation between like the second formula C6H5 and H3 plus and like CO3 to like I'm trying to figure out like what the relation here is and like how you got CO3 2 minus and H2CO3.
How did I get these guys on the bottom you're talking about? Yeah.
Yeah.
Yeah. So in one, these are sort of like two separate sort of situations. So in one situation, if we were looking for the conjugate acid, that means this guy would be acting as a base in that case, and he would be accepting the H plus, which is how we got to the H2CO3. Now, there's other situations where this exact same guy will not act as a base, but will act as an acid. And then in that case, he will produce the other way, which is CO3 2 minus. So it does sort of depend on the situation, but this particular substance, which is bicarbonate there, has the ability basically to act as either an acid or base, depending on the situation. And so, if that is their question.
I'm just kind of wondering uh like if this were like a test, like how would I figure out that it's specifically like bicarbonate, for example?
You would be given HCO3 minus, and it would ask you to write either the formula for the conjugate acid, or it would ask you to write the formula for the conjugate base.
Oh, is that like not related to like the initial question or?
It's not related at all. It's just another example. Yeah.
Oh, okay, all right.
Yeah, no, it's just a secondary example. I just happen to write on that page. Yeah, so they're not related, those two things there. But this is just an example to show you that there are certain things that can go kind of both ways, act either as an acid or a base. And again, those things are what are referred to as amphoteric substances.
Okay, thanks.
You're welcome. Other questions? Okay. So then let's talk about water and water's properties. Water also can act as either an acid or a base, and water itself can actually react with itself. So when water sort of reacts with itself is sometimes what is referred to as the autoionization of water. And in one case, one of the waters is acting as the acid, and in the other case, one of the waters is acting as the base. And we do get a conjugate acid and conjugate base that's produced. So this is sort of what's happening when we have water sort of by itself. We have this sort of constant equilibrium that's happening between basically the waters reacting with each other. And since this is an equilibrium, as we can see here, up here, sort of overall reaction, we can write a K value for this, which would be just like we talked about before. I'm too high on that. Let's try that again. Which would be our products, which would be H plus times our hydroxide, which is our other product, divided by our reactant. But again, here, water is a pure liquid. So this, as we will see on the next slide, is a special equilibrium, which is known as Kw. And it's basically the relationship that happens with water. And it allows us really to figure out, what's going on in the solution in terms of, is it acidic or basic? So really in a solution, these are sometimes what is referred to as the strongest acids and bases you could have, because there's kind of the generic versions here of our base and our acid part, basically, of the solution. And when we look at that, which is known as Kw, it does have a value of 1 times 10 to the minus 14. So Kw is the H plus concentration, the molarity, times the OH minus concentration. The molarity is 1 times 10 to the minus 14. We could use this to figure out the concentration of the acid part and the base part. So again, kind of think of this as the acid part of the solution. This is the base part of the solution. And it's really the same calculation regardless of sort of what you do. You do take H plus, for example, would equal 1 times 10 to the minus 14 divided by the OH minus concentration. Or the other one would be the exact same calculation. OH minus equals 1 times 10 to the minus 14 divided by the H plus concentration. And again, you could use these to figure out, like I said, sort of the base part of the solution and sort of the acid part of the solution. And you can really use those values that you get to figure out whether or not the solution is going to be acidic, basic, or neutral. So if you calculate the H plus concentration and it equals the OH minus concentration, the solution would be neutral. And by the way, that means that this guy's concentration would be something like 1 times 10 to the minus 7 molar at that point. And that would give you a neutral solution. If you calculate the H plus concentration and it is larger than the OH minus concentration, that essentially means that the acidic concentration in that solution is bigger than the basic concentration. And that would tell you that the solution is acidic. And if you calculate the H plus concentration and it's less than the OH minus concentration, that means essentially that the base part of the solution is larger than the acidic part of the solution. It will be basic. This is definitely a place in all these calculations we're coming through that you want to make sure you use your exponent button. So again, as we talked about earlier on in the semester here, you always want to use that exponent button when you are using anything that has scientific notation. And pretty much in this part of the class here with the acid, the pHs, and all those things, we do a lot of logs, inverse logs. And again, you want to push those numbers in correctly. So you would hit 1, Again, your exponent button on most calculators, that should put a 1 and an E. The E stands for the times 10 part. Then you would hit the negative button, not the subtract, and 14. And that should give you a negative 14. And that would represent 1 times 10 to the negative 14. You should not be hitting any multiplication button in there when you're entering in something in scientific notation. Again, make sure that you use your exponent button, which again on most calculators look like that, or it may look like this. And again, some of the newer ones will have the the times 10 to the n. And as I mentioned earlier, make sure that if your calculator does have that one, you typically have to put parentheses around all your numbers that are in scientific notation. Otherwise, again, you will be off, and you'll be even more off when we start using the logs and all that kind of stuff. So if you see yourself off on some of these numbers, but it kind of looks right, it's probably most likely the way that you're entering the number in scientific notation. So make sure that you remember that as we go through these, because it can have some problems for people. So why don't we try one there? What is the concentration of hydroxide if the hydrogen ion concentration is 1.3 times 10, just 1.3 times 10. So take a second and figure it out. Also figure out, is it acidic, basic, or neutral? Okay, so let's take a look here. So again, we want to use Kw, which is H plus times OH minus, and that does equal 1 times 10 to the minus 14. By the way, this is one of those formulas that you will also sometimes see it written. Kw is H3O plus OH minus 1 times 10 to the minus 14. Again, here, exactly the same. I personally will use probably H plus most of the time, but same idea if you put that there. So what we want to do is rearrange this. And by the way, one last thing is this as well. It is a Kw value, and it is temperature dependent, although in most cases, 25 degrees Celsius is what you are dealing with. But just remember that this is technically an equilibrium constant. So if by some chance you're not dealing with 25 degrees Celsius, the Kw will change. You may have to look it up, but I would say probably 99.9% of the problems, even if it doesn't mention anything about temperature, you could assume that it's 25 degrees and that this is the number. But if you do come across a problem where it talks about it being a different temperature and you have to do something with Kw, they probably will give you a different Kw value because, again, it will change with temperature. So in this case, we have the H plus given to us. So we want to find the OH minus, and that would be our Kw divided by our H plus. And that means we have 1 times 10 to the minus 14 divided by 1.3. And that is going to give us 7.7 times 10 to the minus, I think it's 15. Yes, 15. And we do need molarity here, or molar written, again, because it is a concentration. So we do need the units. First off, any questions on the calculation? Okay. So if we want to compare, is this acidic, basic, or neutral, we want to compare the H plus concentration to the OH minus concentration. And in this case, we see that the H plus concentration is larger than the OH minus concentration. So this would be definitely acidic. the solution. Any questions on that particular one there? Okay, so you got
I have a
enough.
question.
Yeah.
Sorry, I'm just a little confused as to how you set up the OH equals KW over H plus. Like, is that an
Yeah, so that's based off of basically this sort of formula, I guess is you could word it. This relationship, the KW equals H plus times the OH minus concentration. So in this case, we were looking for the OH minus concentration. So we would divide the H plus to both sides. Cancels, right? Gives us OH minus equals KW over H plus. And KW is a constant. It is this number, 1 times 10 to minus 14. So that's how we got that. And then this H plus was given to us in the problem.
Oh, okay, I see. Thank you.
You're welcome. Other questions on that? Okay, so why don't you give the next one a go as well? So we're looking, what is the OH minus in this one, and is it acidic, basic, or neutral? Okay, so let's take a look. So same idea here. We're going to use the KW, which is our H plus and our OH minus concentrations, equals our 1 times 10 to the minus 14. In this case, we're looking for the OH minus again. Really, it's the exact same calculation, no matter which one you're looking for. You're basically going to take 1 times 10 to the minus 14 and divide it by the other concentration. So in this case, the H plus concentration was 1.2 times 10 to the minus 6. Again, here, you want to make sure that you punch these guys in correctly. So 1, hit your exponent button, hit your negative button, and hit 14, hit your divide button, hit 1.2, your exponent button, your negative button, and your 6, and hit the equals button. And if you do all that good stuff there, hopefully you end up with something like 8.3 times 10 to the minus 9 are on most people's calculator, because you probably don't have it in scientific notation. You end up with a bunch of zeros here. Something like that, I think. 1, 2, 3, 4. So you might end up with something like that, which you do if you're not in scientific notation. Your calculator might run out of space. But if you put in scientific notation, that's how we actually get to the 8.3 part of the number. At that point, that would be our concentration for hydroxide. So we do need to put the molarity there. And we get 8.3 times 10 to the minus 9. Again, here, you would want to probably change it into scientific notation or something like that, or add an extra 0 because should probably have 2 sig figs, probably based off of this number. At this point, what we want to compare is the H plus concentration to our OH minus concentration, and we want to see which one is larger. So hopefully when you looked at it, you were able to determine that it is the H plus concentration that is larger. 10 to the minus 6 is a larger number than 10 to the minus 9. That also sometimes confuses people, but remember that the negative here is really important because it is an exponent, which means basically with that negative, you're going to go 1.2 and go only 6 places that way, put zeros. But with the other guy, you're going to go 8.3 and go 9 places, which can give you more zeros and a smaller number. So when you have a negative exponent, the smaller number is actually the larger number when you have it in scientific notation. Question on that. So to answer it, I guess it is number 4, looks like the winner there in terms of the answer. Any questions on that, or how to calculate H plus concentration, OH minus concentration, determine if it's acidic, basic, or neutral using KW?
Sorry, can you go over how you determined if it was acidic, basic, or neutral?
So when you want to determine if it's acidic, basic, or neutral, you need to compare the H plus concentration, which is this number. That's essentially the acidic part of the solution, right? And you want to compare the OH minus concentration, which is really the basic part. And you want to see which one is a larger number. So whichever one's a larger number would tell you it is either acidic, basic. If they are both exactly the same number, which means they would both be 1 times 10 to the minus 7, then they would be neutral. But whichever one's larger will be what it is. So in this particular case, when you compare those two numbers, the 1.2 times 10 to the minus 6 versus the 8.3 times 10 to the minus 9, this number here is a smaller number than this number. This one is larger. And since the H plus concentration is larger, that means that this solution should be acidic in this case.
Okay, and that's because it should be on the product side?
It has nothing to do really with products. It's just simply looking at the actual values. So basically, let me see if I can put here. Maybe come back and find somewhere I can scribble. Let me scribble here. So basically, what it just really means when you look at those numbers is what we're talking about. There is really no kind of left side, right side. We're really looking at in a solution how much H plus is floating around and how much OH minus is floating around, the concentration of both of those, and just the straight comparison of those free H pluses floating around or free OH minus floating around based on the numbers that we had in the previous example we were doing. This guy here has a larger concentration than the OH minus concentration. So that's just what it essentially means is, you know, there's more of these guys floating around, right, than there is hydroxide floating around. So because there's more H plus floating around in the solution free, it's going to be more acidic or an acidic solution than a basic solution. And the opposite,
Okay.
if the opposite was true, and you could tell that by the concentration number, if you had a larger OH minus concentration, essentially means you have more of these guys floating around versus H pluses, which means since you have more of these guys floating around freely, it should be basic. So the way you could compare that is by looking at the concentrations like we did and seeing which one is larger, and whichever one is larger will tell you is whether it will be acidic or basic.
Okay, that makes sense. Thank you.
You're welcome. Other questions? Okay. Uh, 1.2 is larger than 8 because those are not actually the numbers. So if we take the actual numbers themselves, and this is what I was talking about in terms of the exponent part. Let me just write it out. decimal way so you can visualize it. So when we say 1.2 times 10 to the minus 6, that is this number here, 0.00000, if I get the right number of zeros there. So that is this number right here, written out in decimal form. When we look at this number, it is 0.12345678883. So when you compare this number to this number is smaller when you actually write it out with all those zeros and stuff like that. So it's much smaller, and that means this guy is bigger, and that's why it is larger. So that's what I was saying before. Really, when you're comparing, if you look at this part of the number, the negative is really important here because it represents these guys. And in this case, when you have a negative exponent, the one that's actually the smaller number is the larger overall number, because you're only going so many places to the left. The one with the larger number means you're going more places to the left, going to put more zeros and make that number smaller. Other questions on that? Okay. Then let us continue on then, I think. So the next thing we're going to talk about, maybe get some things to move around here. So keep drawing pictures everywhere. All right. Wow. So just put X's over everything. Here we go. There we go. We're going to talk about next the pH scale. And the pH scale basically runs from 0 to 14. So when we talk about the pH scale, goes from 0 to 7 to 14, and below 7 to 0, it's acidic. Above 7 to 14 is basic. And 7 sort of your middle point there, and 7 actually is neutral. And 7 is neutral because at that point, as we just saw, the concentration of H plus equals the concentration of OH minus, which means they basically equal 1 times 10 to the minus 7 molar. And if you calculate the pH off of that, that actually gives you a pH of exactly 7. So technically 7 is neutral, dead on the nose is where 7 and neutral is. When we go from 7 towards 0, you're becoming more acidic. When you go from 7 to 14, you're becoming more basic as you head that way. So how do we calculate pH? It is that formula that we see there. The pH is equal to minus the log of the H plus concentration. Again, this is another one where you can substitute H3O plus in there for it as well. So again, where it says H plus, you will sometimes see minus the log of the H plus concentration or minus the log of the H3O plus concentration. Again, same deal. So when we do calculate the pH, as I mentioned, if the solution is neutral, the H plus concentration would be 1 times 10 to the minus 7, which technically would give you a pH of 7. So for this class, so there's no misunderstanding, we will go with a neutral pH of being 7. If it's not 7, it's like 7.1 or something like that, it will be slightly basic. 6.9, it will be slightly acidic. So we'll go with 7. So there's no understanding about where that range may be. So if it's 7, it's neutral. If it's not 7, then it's either a little bit acidic, a little bit basic in that particular case. Acidic is when we were been talking about here, we have an H plus concentration that is larger than the OH minus concentration, which means when you put it into the formula there, you will get a pH that's less than 7. Basic is what we saw as well when you have an H plus concentration that's less than the OH minus concentration, and you will end up with a pH of greater than 7. The relationship between pH and H plus is as the H plus concentration goes down, the pH goes up, and vice versa. As the H plus goes up, the pH will go down. So these, again, are the two relationships there. This guy goes up, pH will go down. And this is really based off of as well that KW relationship, the relationship between H plus and OH minus is an opposite relationship. So as one goes up, the other goes down. So as the H plus concentration increases, OH minus concentration decreases. And as the H plus concentration, the H plus concentration decreases, the OH minus concentration increases. So they basically go opposites of each other. And that's how we know, whether we have an acidic solution, basic solution is because as the H plus goes up, the OH minus goes down. So there's a lot more H plus floating around, which would make the solution acidic, and vice versa. OH minus goes up versus the H plus, a lot more OH minus in that solution, which would make it basic. So let's talk about this formula here and calculators, which always give people problems. So if you have a display calculator, you enter it exactly the way you see it, which is you hit the negative button, not the subtract button. You hit the log button, and then you hit the H plus concentration using your exponent button. If you have a non-display calculator, this formula and the rest of them we're going to see here today, you go the opposite way. You need to start with the number, then hit log, and then hit the negative. If you're not sure if you have a display calculator or non-display calculator, you can hit log on your calculator. And if it says log, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. So that's the way that you can basically recognize it. Any questions on pH? So let's talk about pH though and significant figures. So when we calculate something like pH, the number of decimal places in our pH is equal to the number of sig figs in our concentration value. So this is a little bit different. So let me say it one more time just to make sure. The number of decimal places, not significant figures, but decimal places that you should have in your pH value is equal to the number of significant figures in your concentration. So let's just make sure everybody's calculator is working and all those good things. So let us go with, why don't you calculate the pH? What is the pH of a solution that has an H plus concentration of 1.2 times 10 to the minus 4 molar? So calculate that to the right number of significant figures. So again, if you have a display calculator, you should be hitting the negative button, the log button, and then putting 1.2 exponent, negative button, and 4. If you have a non-display calculator, you should start with the 1.2 exponent button, negative 4, hit the log button, and then hit the negative button. And whichever way you did that, you hopefully will start with just a number first off. You should end up with something like 3.920818754. We'll just start with the number part. Hopefully you got some number on your calculator that looks like that. Any questions first off on the number part of it? So clearly that many numbers is not the right answer, right? So the right answer that you should give based on this question is 3.92. So it should be 3.92. So one more time, what the rule is, this is our concentration value right here. That has two significant figures. This number here has not 2 significant figures, but 2 decimal places. So 2 decimal places here, and that would be the proper way to do the pH for this solution. And by the way, 3.92 would also tell us that this guy is acidic as well. Question on that rule there. Okay. So again, oftentimes people sort of get that confused. So it's not significant figures and significant figures, but it's actually significant figures in the concentration to decimal places in the pH value. Any questions on that? Now, there is similar scale to pH, and we'll talk about that in just a second, but here is the pH scale, and as you can see up here at 14, we got sodium hydroxide, which is a strong base. We got some hydrochloric acid down here towards 0, and that is a strong acid. We have pure water over here, which is 7. Got some vinegar, lemon juice, and stomach acid, which are all acids, so they're acidic. A lot of household cleaners that are basic. Now, if you took some regular water, that's not, say, deionized water, and even some water that you left out for a while, sometimes people are surprised at the pH. It actually probably won't be 7. Yeah, it'll probably be in this area, actually. And that's because as water, especially water that sits out, picks up some CO2 from the air, and before you know it, you have just made H2CO3, which is carbonic acid, and it tends to lower the pH because the H plus concentration comes up a little bit. So sometimes people are surprised if they test sort of tap water or water has maybe been out for a bit. They assume that it probably is 7, but what they find is it's not always 7. It's actually a lot of times more acidic. And again, that's because it's picking up carbon dioxide from the air and forming some more H plus and lowering the pH. That's why years ago, I don't think they do it anymore, but years ago in Chem 50, they used to make you boil your water when you did that experiment, that titration experiment. And the purpose of boiling the water when you did the titration experiment is to get rid of the CO2 in it and bring the pH back up to more neutral. So that used to be a common sort of problem that you used to have. So the pH scale, again, is really the scale that you should look at and you should think about. But there's also other scales that are sometimes used, and one of them is what is known as the pOH scale. And the pOH is calculated, as you can see here, pretty much like the H plus, except the name actually tells you pOH means you need some OH minus concentration. So the pOH is minus the log of the OH minus. You calculate it the same way, so you punch it in pretty much the same way as you do pH. But what you get out is not the pH, it is the pOH. The benefit of using pOH is this relationship here. There's a very nice relationship of if you take the pH and you take the pOH together and you add them, you get a value of 14, which means this is very convenient because if you have, for example, just the OH minus concentration, you can calculate the pOH first, then take 14 minus the pOH, and that will give you your pH value. So it's a very convenient way to kind of go from pH to pOH and back and forth using that relationship. Now, the reason when you have both values, and sometimes this happens, and make sure it doesn't happen to you, if you have the pH value and you have the pOH value, you should always look at the pH value for whether or not it's acidic, basic, or neutral, because pretty much in everybody's head, this is the scale they have in their head. Not the pOH, because the pOH runs opposite, which means if you have a low pH, you will have a high pOH. And vice versa. If you have a high pH, you will have a low pOH. So they run opposites of each other. And the pOH scale, 14 is acidic, around that way, and 0 is basic. So my recommendation is always look at the pH value and not the pOH value, because again, you will get the wrong answer in terms of acidic, basic, or neutral. Also, when you're asked that question, is the solution acidic, basic, or neutral? The answer is just one of those answers. The solution cannot be acidic and basic at the same time. And that happens because when people calculate the pH, they go, oh, this value is less than 7, so it's acidic. Oh, wait, this pOH is more than 7, then it's basic. And they end up saying the same solution is both acidic and basic at the same time. I've never had anybody go with all three, which I guess is good, acidic, basic, and neutral at the same time. But they cannot be both. So always look at the pH. Should only be one answer for that. Is it acidic, basic, or neutral? Again, one of those guys should be the answer. Now, in addition to these formulas that we saw here, the pH, the pOH, so we have our pH. We can also, if we are given the pH value, so if we're given the pH value, we could actually get the H plus concentration from it. So pH, I could get the H plus concentration. And the H plus concentration is the inverse log of the minus pH. So if you're given the pH, you could actually get the H plus concentration directly from that value by taking the inverse log of the minus pH. Now on your calculator, this is actually where if you hit the inverse log, it will usually put the 10 and the caret up on most people's calculators. And then you want to go minus pH. This is, again, why you don't want to be doing this for exponents, because you need to do this for the actual calculation. So most people's calculator, to do inverse log, you have a log button. You usually have a shift or second button top left. Hit them both. That's usually how you get there. And it'll usually pop that 10 and a caret up. You could also do that for pOH. If you have the pOH, again, from it, you could get the OH minus concentration. And that is going to be the inverse log of the minus pOH. And again, that will pop up at 10 and a caret minus pOH usually on your calculator. And that's another way. So those three things, the pH, or four things, five things, the pH equals minus the log of the H plus concentration. The pOH equals minus the log of the OH minus concentration. The pH plus the pOH equals 14. The inverse log of the minus pH gives you the H plus concentration, and the inverse log of the minus pOH gives you the OH minus concentration, along with the KW we saw earlier. These are all important formulas that you do need to know. And the nice thing about all these formulas is it does give you a variety of ways that you can solve the same question. So, you know, you may not even have to use KW at all, or you could use KW and not the inverse log. You know, so there's a lot of different ways you could actually get to sort of the answer in a lot of these problems. And again, just sort of depends on the pathway you choose to do that. Any questions on that there? All right, so let's take a look at some here. The pH is 4.82. Let's just try out all of our calculations here. So in addition to the H plus for this first one, figure out the H plus, figure out the OH minus, figure out the pOH, figure out is it acidic, basic, or neutral. And for this second one, same deal. Let's figure out the H plus concentration. Let's figure out the pH. Let's figure out the pOH and figure out is it acidic, basic, or neutral. That should give you a good run at your calculator and making sure you know how to punch them in correctly. So take a few minutes here and figure out all those things for each of these. Okay, so let's see how we're doing on this. So we'll start with the first one. So in this case, they gave us the pH. So we have the pH given to us. And the pH is 4.82. So really from the pH, there's a few different things you could get kind of from it. You can get the POH pretty easily. So again, the POH would then be 14 minus the pH, and that would give you 14 minus 4.82, and that will give us a POH of 14 minus 4.82. Looks like 9.18 as our POH. And that is from the relationship of the pH plus the POH equals 14. Now, since we have the pH, we can also directly get the H plus concentration from it. The H plus concentration would be the inverse log of the minus pH. So on your calculator, that's going to be 10 and caret. Make sure you make it negative 4.82. And if you do that, minus 4.82, that is 1.5 to the minus 5. We do need molarity here because it is a concentration. And that takes care of, so far, the POH. We just did the H plus. Now that we have the H plus, we could use KW like we used before. We also have the POH as well. So I'm going to do the POH kind of the newer way, which is going to be the same calculation. The OH minus will equal the inverse log of the minus POH. That is going to give us 10 to the caret minus 9.18. And again, if you use KW, you should get pretty much the same answer. Might be slightly different if you did some weird rounding or something like that, or a little different rounding, but it looks like it is 6.6 to the minus 10. Again, also needs the molarity there since it's a concentration. And lastly, here we have our pH, which is 4.82, and that is the one you should look at. So a pH of 4.82 is less than 7, which means this guy should be acidic. Any questions on any of those parts there? I also would like to point out that my pH value here had 2 decimal places. That means when I did my concentration, it had 2 significant figures. So as you go backwards as well from pH or POH back to the concentration, you should follow the same sig fig rules that we were talking about. So because my pH had 2 decimal places, that tells me that my concentration should have 2 significant figures. Any questions on any of those there?
Yeah. Which numbers did you compare besides 4.82 to see if it was acidic?
I didn't really have to compare. You don't really have to compare anything if you have the pH value, because of the pH scale is 0 to 7 to 14. Less than 7 is acidic.
Oh, got it.
Above 7 is basic, and if it's 7 is neutral. So really, if you have the pH, the benefit of just having the pH is you just need to see where it falls on the scale. You could also, if you wanted to, the harder way, I guess, in this case, is you could look at both of these numbers here, like we did earlier, and you could compare which one's larger. And what you'll see is this guy's larger, which is the H plus concentration, which would also tell you it's acidic. But the easier move, if you have the pH value, would be just to see where it falls on the pH scale, and make sure that you always look at the pH value, not the POH value. Other questions? Okay, so let's take a look then at the second one we got going on there. And in this particular one, we're given the OH minus concentration. So again, you have a variety of ways you can get to the answers here. One way is not better than the other per se, but so since I have the OH minus concentration, I'm going to actually calculate the POH first because I can. And that's going to be minus the log of the OH minus concentration, 2.5 times 10 to the minus 7. And that would give me something like 6.60 as my POH. Now that I have my POH, I could use that relationship of the pH plus the POH equals 14, which would tell me that my pH would be 14 minus 6.60. And if I take 14 minus that, gives me 7.40. So that takes care of the pH, takes care of the POH. So I have H plus left over. And again, at this point, do it. Want to go back to the KW, you can do that. Go 0.0 times 10 to the minus 8 molar. You also, because you have the pH as well, you could have done what we did before, which would be the H plus is equal to the inverse log of the minus 7.40. That's like a 10 and a caret. And that should end you at the same answer as what we got there. And again, you could do it either way. They're both basically the same here. And at that point, last thing is this guy is going to be slightly basic, just above 7. So we'll go with slightly basic on that particular one. Questions on any of those sort of calculations there? So again, just to make it simple, so there's no question of, well, it's only 7 point something or 6 point something. Like I said, we'll just keep it very simple. Hardcore definition of neutral, pH of 7. So it has to be 7 for it to be neutral. Question on that? Okay, so I think got one more here to practice. All right, so give that a go. We have the H plus concentration given to us. We wanted the pH, POH, and OH minus concentration. So see what you come up with, and is it acidic, basic, or neutral as well? Okay, so let's take a look here. So again, in this case, as we've been seeing, there are multiple ways you could kind of approach it based on what's given to you. So in this case, we have the H plus is 3.5 times 10 to the minus 6. So many ways you could start. You could use KW to get the OH minus. I'm just going to go with the pH here. So the pH is minus the log of the H plus, and that's going to be minus the log of 3.5 times 10 to the minus 6. Again, make sure you use your exponent button here. 3.5 exponent minus 6. Going to give you a 5.46, looks like, as your pH. Once you have the pH, you could subtract 14 from it, and that will get you your pOH. So that'll be 14 minus 5.46. And if you do that, that will get you 854 as our pOH. At that point, that's the pH, the pOH. To get the OH minus, again, you can use KW. You can use that the OH minus is equal to the inverse log of the minus pOH. So again, when you pump that into your calculator, punch that into your calculator, it'll put a 10 and a caret, negative 8.54. Don't forget the negative there. And looks like we'll go with 2.9 times 10 to the minus 9 molar. Again, need molarity there. And that would be the OH minus concentration. And again, here, if we want to know if it's acidic, basic, or neutral, also have a couple ways you could do that. You could compare these two numbers, which might be a little bit more difficult than just simply looking at our pH value. And our pH value is less than 7. So we know that this solution is acidic. In this case. Question on how to calculate pH, pOH, H plus concentration, OH minus concentration, figuring out if it's acidic, basic, or neutral. Any questions on any of that? Okay, so yeah.
Actually, I had a question. Can you work out the OH the other way?
Sure, we're using KW.
Oh, so is it just KW over OH?
It would, well, we're looking for the OH minus, so it would be the
Oh.
KW over the H plus. Right?
Okay. Got it.
Yep.
Thank you.
And you should get the same answer, maybe slightly different if you did a little bit of rounding, but pretty darn close to the same answer as what we got here. Other questions on that?
Thank you.
Welcome. You're welcome. Other questions? Okay. So obviously you need to be able to do all that. As I mentioned earlier, and we've been talking about next week on Thursday is our first exam covering chapters 12 and 13. A reminder that no formulas will be given to you, but constants are conversions and a periodic table if you need. I'm not even sure if you need one, but it'll be provided for you. We will take it during lab time next week. So on Thursday during lab is when we will take it using probably proctorial, kind of like the quiz. So you'll need that set up. Again, you have a week, so make sure you arrange it. So again, it's not just your head that I see, but try to do your best to get both you and kind of your work area, your paper area in the picture as best as you could do. Again, if that requires you to sit to the side of your computer, that requires you to push your laptop back or something like that. You know, try to do your best to get a little bit of more than just top of the head. So we'll take it during lab. We'll open up around lab, and obviously it'll be open up for only the period of time during lab. And you're expected to start the exam at the start of lab as well. We will continue lecturing on Tuesday. Today in lab, we're going to start the next experiment. So we'll talk about the next experiment, which is equilibrium. And other than that, we'll stop here for now for lecture. So I'll see everybody at 11:30. So make sure if you didn't put here in the chat box that you do that as well. All right, I'll see you in a bit.